Hi, welcome once again to our YouTube channel. Thanks for subscribing to our channel. Really appreciate it. Quickly want to look at some sample questions for our quantitative analysis, which is in the Neco 2025, the ongoing examination, talking about some titration questions. We want to use these questions to actually prepare ourselves in expectation of possible questions that we might be coming across in the Neco practical examination. So this year's examination, Neco has given us some specimen that we'll be using for our experiment. We have our sample A, which is the acid, to be HNO3, and if we are to calculate the molar mass of HNO3, using this as our study, we have H to be 1, we have N to be, we have our N there to be 14, we have our O to be 16. So for using this now, we have this here, our H, we have it to be 1 plus our N is 14 plus our O is 16, or 16 times 3. You can see because our oxygen is 3. So what we'll be having there is going to be 15 plus, we have 15 plus 48, and that is going to give us 63. So 63 grams per mole is going to be the molar mass for this particular substance, 63 grams per mole. And then for our sample B, will be having sodium transcarbonate. That is what we'll be having for our sample B. So for that, what we'll be having there, the molar mass of sodium transcarbonate, we'll be having for sodium, let me quickly put the values here. The mass is the mass of sodium. We have the atomic mass of sodium, we have it to be 23. We have that of carbon to be 12. I think these are the remaining two that we have here that has not been added here. So using this now, we have the molar mass to be sodium 23 into plus our carbon, which is 12, plus our oxygen, which is 16, in 3 places. So we have 46 plus 12 plus 48. 46 plus 12 plus 48. And that is going to give us, we have it to be 106 grams per mole. That is going to be the mass, the molar mass of sodium transcarbonate. So let us see what the equation for this reaction will be. If we are using HNO3 and sodium transcarbonate, what will be the reaction? What will the reaction be looking like? So equation for the reaction will be, so for the equation now, I'll be having HNO3 plus sodium transcarbonate to give us sodium transonitrate plus water, and then carbon dioxide. This is what the reaction will be looking like. So to balance the reaction now, because the reaction doesn't seem balanced, so we're having 2 here. If we add 2 to this place here, that will make us put 2 here also to balance the reaction. So that tells us that our substance here, our reacting masses and the reacting substances, acid and base, in ratio 2 to 1. We have our acid to be in ratio 2 and our base to be in ratio 1. So with this now, we have our balanced equation for the reaction. So now let's look at some things. These are possible formulas that could be used or that could come handy in answering quantitative analysis questions or volumetric analysis questions talking about the titration. So we have a couple of them here talking about the mass concentration, which is molar concentration times molar mass, and that can be substituted. We get the formula for molar concentration as well. So we have all of these formulas here. We can quickly look at them. I do not want to waste much of our time looking at them, so we have them here. You can see them. These are all formulas. And then after that, we have this here, talking about some indicators that are oftentimes used in titration. We can see them, indicators that are used in titration. All of these are indicators, methyl orange, and their color in different solutions, different compounds, be it acid, base, or in neutral reactions at end point. So we have methyl orange, phenolphthalein, bromothymol blue. These are possible useful indicators. And also we have this here, talking about titrations and the most suitable indicator that could be used for all of them. So for strong acid, strong base, we have N indicator being used. N indicator is suitable for this type of reaction. But if it is a strong acid to a weak base, oftentimes we use methyl orange, and then weak acid to strong base, we use phenolphthalein. And for weak acid versus weak base, what we also look at in this particular reaction, because the reaction is not very productive, it doesn't have very suitable indicators. So that is just what we quickly want to look at, talking about the titration. So going to the class now, we said that this is the reaction that we want to look at, talking about our acid being HNO3 and our base being the thiazocarbonate. Here are some sample questions that we want to use in today's examination, in today's reaction. So these are some sample questions. We have our sample question 1 here, which is reading: A is a solution containing 0.1 mole per dm cube HNO3. B was prepared by diluting 1 centimeter cube of a saturated solution of sodium thiazocarbonate at room temperature to 1000 centimeter cube. So we are told to put this into our burette and titrate it against 25 centimeter portions of the B using methyl orange as indicator. Repeat the titration 3 more times and then get your table. From the table now, we are told to calculate all of this here that we have here, and this is the reaction that is used for this particular the equation that is used for this particular reaction. So 1, we are told to calculate B in mole per dm cube. 2, solubility of sodium thiazocarbonate in moles per dm cube. 3, mass of B, which is obtained by evaporating 1 dm cube of the saturated solution to dryness. And then 4, volume of carbon dioxide at STP, which would be liberated from 1 dm cube of B. So we are assuming our volume of acid used to be 23.10 in this particular question. So going to that now, this is what we'll be having. Concentration 1, concentration of B in moles per dm cube. That's the first thing we have to calculate there. So the formula to use is this. The formula to use, we have CAVA over CBVB equals NA over NB. So if you cross multiply now to make it a straight line equation, we'll be having CAVANB equals CBVB NA. And from here now, since we are looking for B, we could make CB subject of the formula. So CB equal CAVANB all divided by the coefficient of CB, which is VBNA. So from our question, we know our CA is 0.1. It is there in the question. And then we have our VA. We said we are using 26.10. And our Na, number of moles of acid, is, sorry, this one is supposed to be NB. Our NB, number of moles of acid, is 1, and then divided by our VB, which is 25, that is gotten from the volume of pipette that is used, by multiplied by the number of acid, number of moles of acid, which is 2. So if you calculate this now, what we'll be getting will be 26.10 divided by 50, and that is going to give us 0.0522, and these three significant figures now will give us 0.0522 mole per dm cube. So this is the answer that we have for that particular first question. So going to the second question now, we have this 2. Solubility of sodium transocarbonate in mole per dm cube. Solubility of sodium transocarbonate in moles per dm cube. Notes: we do not know our C1, that is what we are trying to calculate. We do not know our C1, but we know our C2 to be what we just finished calculating, 0.0522 moles per dm cube. We knew that from the question, the volume that was diluted with 150 centimeter cube, and then our V2 is 1000 centimeter cube. 1000 centimeter cube. So using this information now, formula to use, we'll be using C1V1. C1V1 equals C2V2. We're looking for C1, so let's make that subject of the formula. So this gives us this here. So when we input our parameters, we'll be having 0.0522 multiplied by our V2 from here, which is 1000, divided by our V1, and our V1 there is 150. So this is going to give us 0.348 moles per dm cube. So this is the answer that we get for that second question. And then we move to the next question, which is question 3. Still in question 1, Roman numeral 3, we have mass of B obtained by evaporating. Mass of B obtained by evaporating 1 dm cube of the saturated solution. To dryness. So from this now, the formula to use is this. We have mass equal, we have the molar mass of sodium transocarbonate multiplied by solubility of B, and then multiplied by the volume given in dm cube. Volume given in dm cube. So with this now, we know that molar mass of the substance, the molar mass of sodium transocarbonate is 106, multiplied by the solubility of B, which was what we just calculated, and we calculated it to be 0.348. So that is what we are using, 0.348, and multiplied by volume given in 1 dm cube. This particular substance was diluted in 1000 centimeter cube, which is equal to 1 dm cube. So multiplied by 1, and so this is giving us 36.888, and these three significant figures now, it becomes 36.9 grams. So that is the answer to this particular question. And then the next one, we have volume of carbon dioxide. That is what you are told to calculate. Volume of carbon dioxide liberated. volume of carbon dioxide liberated. Now let's look at this. If 1 mole of sodium trisulcarbonate equals 1 mole of carbon dioxide. You can remember that we had something similar to that in this reaction here. Look at it here. Our sodium trisulcarbonate is in 1 mole and it is giving us 1 mole as well of our carbon dioxide. You can see that this one here is 1. You do not need to write it. This is in ratio 1. Here is ratio 1 and here is ratio 2. So that is how the masses are. So with that now, that is what we are using to answer this question here. So if we have 1 mole of sodium trisulcarbonate to be 1 mole of carbon dioxide, then from this that we calculated here to be the mole of trisulcarbonate, we have it to be 0.0522. We can say 0.0522 moles of sodium trisulcarbonate will give us also 0.0052 moles of carbon dioxide. And then from that we can see that X equals 0.0522 multiplied by 1 divided by 1. That is if you choose to cross multiply. So we'll be having something like that. So invariably what we are saying is that we'll be having this here to be 0.0522 moles of carbon dioxide. So using that now, let us now calculate what we actually want to calculate. Volume of carbon dioxide equals, we have the mole of carbon dioxide, which was what we just calculated, mole of carbon dioxide multiplied by the molar volume of a gas. So the mole of carbon dioxide, we have it to be 0.0522 multiplied by the molar volume of a gas is 22.4 dm cube. So this is going to give us 1.16928. So to three significant figures now, is giving us 1.17 dm cube. So this is the final answer for that particular question. Here we have our question 2. A is a solution containing 5.67 grams of HNO3 in 1 dm cube. B is a solution containing 8 grams per dm cube of a mixture of sodium trisulcarbonate and sodium trisulnitrate. Put A into the burette and titrate to 25 cm cube using methyl orange as indicator, and then you repeat your titration. Using this same thing here, this same equation as the equation for the reaction, we are told to calculate the volume of acid used. Then from that and the information that has been provided above, we have to calculate 1. Concentration of A in moles per dm cube. 2. Number of hydrogen ions in 1 dm cube of the A. Mass of HNO3 in 20 cm cube of solution, and then volume of distilled water that should be added to 25 cm cube of solution or solution A in order to dilute it 5 times. So for this question, we are assuming our average titral value to be 26.40. That is what we are assuming to be the average titral value in this particular question 2 now. We have the first thing to be calculated there to be concentration of A in mole per dm cube. 1. Concentration of A in moles per dm cube. So the formula to use, the formula that we have to use this molar concentration equals mass concentration divided. So from that now, Ca, which is our molar concentration, is, from the question we're given 5.67. You can see it here that the mass concentration of our A is 5.67 gram in 1 dm cube. So 5.67 divided by the molar mass of A, we already calculated it previously to be 63. And so from this, we have it giving us 0.09. So to three significant figures now. To three significant figures, it becomes 0.0900 moles per dm cube. So that is our answer for the first question in that particular series. And then question 2, question Roman numeral 2, we have to calculate the number of hydrogen ion in 1 dm cube. Number of hydrogen ion in 1 dm cube. To do that, this is the formula that we have to use. Formula to use, we have number of hydrogen ion equals, we have Avogadro number, Avogadro's number multiplied by the basicity of A multiplied by the concentration of A in mole per dm cube, and then also multiplied by the volume of the substance given in dm cube. Volume in dm cube. So we have this here giving us, for our Avogadro constant, we have it to be 6.02 times 10 raised to the power 23 multiplied by basicity of the substance is 1 multiplied by the concentration of A in mole per dm cube. We have it to be 0.0900 multiplied by the volume in 1 dm cube. So all of this gave us this here to be, we have it to be 5.418 multiplied by 10 raised to the power 22. And these are the three significant figures now. The three significant figures, it gave us this 5.42 times 10 raised to the power 22 aeons. So that is the answer for that particular question. I'm going to talk about the third one. We have this here. We have this mass of HNO3 in 20 centimeter cube of solution. Mass of HNO3 in 20 centimeter cube of solution. The formula that is applicable to this, we have mass equal the molar mass of HNO3 multiplied by the concentration of A multiplied by the volume given in 1 dm cube. Volume given in dm cube. So we have looking like this. Mass equal, our molar mass for HNO3 is 63 multiplied by our Ca is 0.0900 multiplied by our volume given in 1 dm cube. We have it to be 20 divided by 1000. Remember, we're looking for 20 centimeter cube in 1 dm cube. So from that now, we have it looking like this. Mass equal 63 times 0.0900 times 0.02. All of this is amounting to 0.1134. And then to three significant figures now. We have it giving us 0.11, 0.11, 3 grams. So that is the final answer for this particular question. And then we move to the last question there, talking about the volume of distilled water. Volume of distilled water that should be added. Okay, distilled water, this is the question here. So you should calculate the volume of distilled water that should be added to 25 centimeter cube of solution A in order to dilute it 5 times. That's the question. So distilled water that should be added to 25 centimeter cube of solution in order to dilute it 5 times. In order to dilute it 5 times. So for this now, let's quickly take notes. Note that we have our V1 will be initial volume, and that is 25 centimeter cube. Our V2, we have it to be the final volume, which is unknown. We have dilution factor. And the dilution factor is what? Times 5. So volume of H2O equals initial volume multiplied by dilution factor minus initial volume So this is what we are doing. We have 25, which is the initial volume, 25 multiplied by dilution factor, which is 5, then minus 25. So this is giving 125, then minus 25 here. So it is giving us a total of 100. Giving us 100. So we have 100 centimeter cube to be used in diluting 25 centimeter cube of a substance 5 times. So that is about question 2. And then we move to question 3. So our question 3 there says A is a solution containing 6.3 grams per dm cube HNO3 acid. B is a solution containing 4 grams of impure sodium trisulcarbonate in 500 centimeter cube. We have to do the titration, carry out the titration using 25 centimeter cube of the B and methyl orange as an indicator, and then following the same equation for the reaction that we have been doing from the past. So we have all of this as the question that we have to follow to answer. 1. Concentration of A in mole per dm cube. 2. Concentration of B in moles per dm cube. 3. Percentage of pure sodium trisulcarbonate in mixture. And then 4. Volume of the gas involved at STP. So for this question, we are making use of average titral value to be 26.20. That's what we are using for the average titral value of this particular question, 26.20. So question 3. So 1, we're calculating concentration of A in moles per dm cube. In moles per dm cube. So to do that now, we are going to be using this here. From the question there, we have the mass concentration of A. The mass concentration of A, we have it to be 6.3 grams per dm cube. So we are going to make use of that. mass concentration of A equals 6.3 grams per dm cube. So the molar mass of A we said is 63 grams per mole. So having that, the formula to use now, we have molar concentration equals mass concentration divided by molar mass divided by molar mass. So doing that, we'll be having 6.3 divided by 63, and that is giving us 0.100. So our final answer for that question there is 0.100 mole per dm cube, since we are told to calculate the molar concentration. And then 2, we are told to calculate the molar concentration of B in moles per dm cube. That is what the second question they told us to calculate, concentration of B in moles per dm cube. So this is how we go about that. Formula to use, we are using CAVA over CBVB equals NA over NB. So if we cross multiply, we'll be having it to look like this: CAVANB equals CBVB NA. And so making CB subject of the formula now, we have it to be CAVANB divided by the coefficient of CB, which is VBNA. So from that, we have our CA, we just calculated it to be 0.100 multiplied by the volume of acid, we said we are using, multiplied by 1, which is the number of moles of acid, as a number of moles of base, divided by the volume of base, which is 25, multiplied by number of moles of acid, which is 2. So that will give us, we have 2.62 divided by 50. So that is giving us 0.0524. So our final answer is 0.0524 mole per dm cube. That is our final answer for this question. And so we move to the next question, which is question 3. Roman numeral 3. There it is asking us to calculate the percentage of pure sodium transcarbonate in the mixture. So percentage purity, that's how we go about this. Percentage purity is what we want to calculate of sodium transcarbonate in mixture. So firstly, we need to know the mass of the B. We need to know the mass concentration of B. So to do that now, mass concentration equal molar conc times molar mass times molar mass. So that is giving us this here. We have it to look like this. Let me write this in full so we don't get confused. Molar mass. So that is giving us 0.524 times 106, which is the molar mass of sodium transcarbonate, and this is giving us 5.5544 to 3 significant figures now. To 3 significant figures, it is giving us 5.55 grams per dm cube. So from this now, we are now to look at calculating the percentage purity proper. So percentage purity equals, we have mass concentration of pure substance over mass concentration of impure substance multiplied by 4 divided by 500 multiplied by 1000 over 1. So this is giving us 8 grams per dm cube. So therefore, percentage purity from this formula that we wrote here, this particular formula, percentage purity equal 5.55, which was what we got here, 5.55 grams divided by 8 multiplied by 100 over 1. So that is giving us 69.1%. So this is our percentage purity of sodium triisocarbonate. And then the next question there is the fourth question, which is asking us to calculate the volume of carbon of the gas evolved at STP. The gas evolved at STP is carbon dioxide. So the volume of that gas is what we want to look at right now. Volume of carbon dioxide evolved at STP. Evolved at STP. So we have it to be this. 1 mole of sodium triisocarbonate, 1 mole of sodium triisocarbonate, which equals 1 mole of carbon dioxide. You can see that in the equation like I showed us earlier on. So therefore 0.0524 moles of sodium triisocarbonate equals 0.0524 moles of carbon dioxide. So from that now, volume of carbon dioxide equals the mole of carbon dioxide multiplied by the molar volume of gas. So that is here giving us 0.0524 multiplied by 22.4. So eventually that is going to give us 1.17376. And these three significant figures now, the three significant figures is giving us 1.17 dm cube. That is the amount or the volume of carbon dioxide that is evolved at STP. So question 4 now, it says A is 0.1 mole per dm cube HNO3 and B is a solution that contains 8 grams per dm cube of a mixture of sodium triisocarbonate and sodium triisonitrate. So we have to carry out the titration like we have been doing in the past and answer the questions that follow. So question 1 there says concentration of sodium triisocarbonate in mole per dm cube in B. 2 is concentration of sodium triisocarbonate in grams per dm cube. 3 there says mass of sodium triisocarbonate in the mixture. 4 says percentage purity of sodium triisocarbonate in the mixture, and 5 is percentage impurity of sodium triisonitrate in the mixture. For this particular one, we are going to be using 26.00 centimeter cube as our average tetra value. So question 4. Question 4. What we have there for question 1, it says molar concentration of B. Molar concentration of B. That is what we want to calculate. The formula to use. The formula to use, we have to use this CAVA over CBVB equals NA over NB. This formula is very, very important, so please try as much as possible to memorize it. So when we cross multiply, we'll be having CAVNA equals CB VB NA. And since we are looking for concentration of B, so we have CB equals CAVANB divided by the concentration of CB, which is the coefficient of CB, which is VBNA. And so here we have it to be this. Our CA, we have our CA to be 0.1 multiplied by 26.00 multiplied by 1, which is our number of moles of base, and then divided by the volume of base, which is 25, multiplied by the number of moles of acid, which is 2. So that in turn is giving us 2.6 divided by 50. So calculating this now, 2.6 divided by 50 is giving us 0.052 to 3 significant figures. Now it will be giving us 0.0520 moles per dm cube. So that's the answer to that particular question. And then the next question there is asking us to calculate the concentration of B, the mass concentration of B in the substance. Mass concentration of B, of sodium tricarbonates in B. Mass concentration of sodium tricarbonates in B. So the formula that we are to use for this, we have mass concentration equals molar concentration times molar mass. That is what we'll be using for this. So we know that the molar concentration is what we just calculated here to be 0.0520 multiplied by the molar mass of sodium tricarbonates is 106. So that is giving us 5.512 to 3 significant figures now. It is giving us 5.51 grams per dm cube. So that is our answer for that second question. And then moving to the next question now, asking us to calculate the mass of sodium triazonitrate in the mixture. Mass of sodium triazonitrate in the mixture. Mass of sodium triazonitrate in mixture. So this is how we do that. The formula to use, we use mass of mixture. Mass of mixture equals mass of sodium tricarbonates plus mass of sodium triazonitrate. Therefore, we can have mass of sodium triazonitrate, since that is what you are looking for. Mass of sodium triazonitrate equals mass of mixture minus mass of sodium triazocarbonate. So since we have those values, we have it to be 8 minus 8.51, which is what we just calculated now. So that is giving us 2.49 to 3 significant figures. Always leave your answer in 3 significant figures. So that's giving us 2.49 grams. So that is the mass of sodium triazonitrate in the substance. And then calculating percentage purity now. That's the next question. We are going to calculate percentage purity of sodium triisocarbonate in the mixture, and then 5 percentage impurity of sodium triisonitrate in the mixture. So 4 percentage purity of sodium triisocarbonate in mixture. Formula to use: we have percentage purity equals mass of pure substance, mass of pure sodium triisocarbonate divided by mass of impure divided by mass concentration of the mixture multiplied by 100/1. So percentage purity now equals 5.51 divided by 8 multiplied by 100/1. And so this is giving us 68.875. So 3 significant figures now. We have it to be 68.9%. And then calculating percentage impurity. Percentage impurity of sodium triisonitrate. Percentage impurity of sodium triisonitrate in the mixture. So the formula that we will use, formula to use, we have percentage impurity equals 100 minus percentage purity. So since we just calculated percentage purity, we can easily do this one. 100 minus this here, which is 68.9. And so that is giving us our answer to be 31.1 percentage. So this is the percentage impurity of the substance. Percentage impurity of sodium triisonitrate in the substance. So that is about question for question 4. To question 5 now. The question there says A is a solution containing 0.1 moles per dm cube HNO3, and B contains 3.75 grams of sodium triisocarbonate in this particular substance there in water in 250 centimeter cube solution. Put A into the bracket, into the red, and titrate like we are used to doing in titration, and use methyl orange as indicator. Carrying out titration, find your average titral value and answer the questions that follow suit. The first question to calculate there is the concentration of B in mole per dm cube. The second one is concentration of sodium triisocarbonate in grams per dm cube. That's the mass concentration. And then 3, the number of molecules of water of crystallization in the hydrated salt. And 4, percentage of water of crystallization in the hydrated salt. So for this one, we are going to be using 26.30 as our average titral value. Question 5. The first question there, we have to calculate the concentration of sodium triisocarbonate, concentration of B in moles per dm cube. So to do that, let us first do this. So we have from the question now, from the question, of sodium triisocarbonate in this, we have it to be 3.75 divided by 250 multiplied by 1000 over 1, and this here is giving us 3750 divided by 250 to give us 15 grams per dm cube. So that is what we have there. And then we have the molar mass. Molar mass of sodium triisocarbonate to be 106 grams per mole. So now that we have this, let us now calculate what we actually want to calculate. Concentration of B in mole per dm cube. So formula to use: we'll be using CAVA over CBVB equals NA over NB. So when we cross multiply, we'll be having it looking like this: CAVANB equals CBVB NA, and then making CB subject of the formula. CB equals CAVANB over coefficient of CB, which is VBNA. So having done this now, we have this here. So CB equals 0.1 from the question, 0.1 times 26.30, which is what we are using for our average volume of acid used, divided by the volume of base, which is 25, times the number of moles of acid, which is 2. So that is going to give us 2.63 divided by 50, which equals 0.0526. So three significant figures now, it is giving us 0.0526 moles per dm cube. So that is the answer to that question. And then to the next question now: concentration of sodium triisocarbonate in grams per dm cube. Concentration of sodium triisocarbonate in grams per dm cube. So formula to use: we have mass concentration of sodium triisocarbonate equals concentration of B, that's it, molar concentration of B times the molar mass of sodium triisocarbonate. So doing that now, we have the mass concentration of sodium triisocarbonate to equal 0.0526 multiplied by 106, and that gives us 5.5756. And then to three significant figures now. It will be giving us 5.58 grams per dm cube. That's the answer. Then we move to question 3. Question 3 that says number of molecules of water of crystallization in dehydrated salts. number of molecules of water crystallization in the hydrated salt. So formula to use. We'll be using mass concentration of hydrated salt divided by the mass concentration of anhydrous salt multiplied by, we have the molar mass of hydrated divided by the molar mass of anhydrous. So with this now, is 15 divided by 5.58 equals 106 plus 18x divided by 106. And then when we cross multiply, what we'll be having there will look like this. 5.58 into bracket 106 plus 18x equals 15 into bracket 106. So when we expand this bracket here now, 5.58 into bracket 106 plus 18x, that will give us 591.48 plus 100.44x. 100.44x equal 1590. And then when we collect like terms now, collecting like terms, we have 100.44x equals 1590 minus 591.48. So this is giving us 100.44x equals 998.52. So when we make x subject of the formula now, x equal 998.52 divided by 998.52 divided by 10044, and that is going to give us this. We have 9.941, which is approximately 10. So that is the amount or the number of moles or the number of molecules of water crystallization in hydrated salt. So that's the answer, which is the last question that we have. It says percentage of water crystallization. Percentage of water of crystallization in hydrated salt. The formula to use for that, we have percentage of water of crystallization equals, have it to equal, let me put it here, mass of hydrated minus mass of anhydrous. Mass of hydrated minus mass of anhydrous divided by mass of hydrated divided by mass of hydrated multiplied by 100/1. So from this now, percentage of water crystallization equals 15 minus 5.58 divided by 15 multiplied by 100/1. So here we'll be having 9.42 over 15 multiplied by 100/1. So that gives us 942 divided by 15, which equals 62.8, approximately 63. So that is the percentage of that substance. So percentage of water of crystallization is 63%. So that is about the questions that we can take for this particular tutorial session for talking about the titration aspects of the Neco 2025 titration. Please try as much as possible to go through the sample questions, practice them, rehearse, get more questions and practice, and hopefully you come across something here that will be able to help you in your examination. Thank you very much for coming along with us. It's a wrap for today.